Let's look at some more examples. From an AP exam, I see. Let R be the region in the first quadrant. That's important. Under this curve, y equals 1 over square root of x, for the interval 4 to 9 for x. Find the volume of the solid whose base is the region R, base is the region that we're going to graph, whose cross sections cut by planes perpendicular to the x-axis are squares. So let's begin with this graph. So if we're only graphing from 4 to 9, maybe we plug in some points and figure out the y values. So 1 over the square root of 4 is 1/2. So 4, 1/2. Notice I spread out the y-axis to help us maximize our region. All the way up to 9. So 1 over the square root of 9, well, the square root of 9 is 3, so that's 1/3. So 1/3 is going to be here, since that's half, and that many blocks will make 1/3. So 5, 6, 7, 8, 9 is right here, so up to this point. Now I know that these rational functions, the way that they behave is coming down from up here, looking approximately like this. So that's how I'm going to connect that. So it says the region under this curve. So from only 4 to 9, looking from 4 just to 9 and under this curve, and only in the first quadrant. So as I shade, I'm not shading anything below the x-axis because that would be out of the first quadrant. Hence just the clip of the first quadrant graph. So this is the base of the solid. The cross sections, we were told, are cut perpendicular to the x-axis. So I like to show a bird's eye view of one of those slices. There it is, one of those slices. Now this is only a bird's eye view. It's difficult to get a good idea of what this looks like. So I like to take out that view and see it as a frontal view. And it says that cross section is a square. Now I remind myself that if I'm finding volume, volume is the integral of the area of one of the cross sections, the area of a slice. And I know that if I am taking my slicing perpendicular to the x-axis, that's going to require me to use dx, being with respect to x. So I have a square. If I need the area of the slice, and the slice is a square, I need the area of the square. Well, what are we going to call this length that went from here to here? Well, it's along the base, so I like to call that b. Call this length from here to here the base of that slice, call it b. Remember, a square is equilateral, so this side we should also call b. The area of the square, b squared, or length times width, but of course the length and the width are the same. Well, we need to know what b is in terms of x. Remember, if it's a length that's going up and down in our graph, we're measuring from the top to the bottom. So if we're measuring from the top to the bottom, we're doing top minus bottom. The top function is the 1 over square root of x function. The bottom is y equals 0. So really our b is just 1 over square root of x. We can now go ahead and plug it into our area equation, and we get 1 over square root of x squared, or just 1 over x to simplify it. Now that we know the area of our slice, we can go ahead and plug it into our volume. So our volume equals the integral of the area, 1 over x, with respect to x, and I look for my limits. If everything's in x's, I'm going to say, well, where does the x start, and where does the x value where the region ends? So 4 to 9. Let's go ahead and solve this one quickly because it's easy to do. 1 over x, natural log of absolute value of x. It's actually easier to do this than to go grab my calculator. Natural log of 9, we'll plug in first, natural log of 4, and we can condense this using natural log properties. Cool. Let's look at a few more. Find the volume of the solid whose base is bounded by those three curves. Let's start with that. Let's start with y equals x cubed. We'll start at 0, 0. Then over 1 up 1. Notice how I'm counting on my y-axis and my x-axis. Over 2 and up 8. And I'm taking a glance at what else I'm going to have to plot. So I'm not going to waste my time going in the other direction since I know the other lines are y equals 0, that's here, and x equals 2, and that is here. So if my shaded region has to touch all those parts, I know I don't have to graph anything further of y equals x cubed. So let's make sure that we lightly shade our region so that we can still easily see those three lines. Okay, let's read the rest. Cross sections are taken perpendicular to the y-axis. Okay, so I'm going to slice this way. So I'm just going to take a representative slice right here. Of course, we know there are an infinite amount of slices here, 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 here. I can keep slicing, but I'm just going to take one representative slice. So just one of these slices. And I'm going to look at one of these slices as a frontal view. They are squares. So again, like the previous one, we have a square. And again, I like to call the length of the square b because it goes along the base of the solid. So I'm going to call that length b. And just like we did in the last one, the area of a square is side squared. I'm calling it b, so b squared. This time, however, to measure our b, our base length, it's going left and right. So I have to go right minus left. Now, always remember what our goal is. If we're finding volume, we remember that volume is the integral of the area of a slice. How do we know with respect to x or y? Well, our slices are taken perpendicular to the y-axis. So therefore, it's going to be with respect to y. Right minus left is another indicator that it's going to be with respect to y. So let's go ahead and figure out what is the function on the right. Well, on the right, that is x equals 2, so 2. On the left, that is x equals, I don't have that yet. I just have y equals x cubed. Let's change that to x equals. Okay, now I'm ready. So on the right, I have x equals y to the 1/3 or cubed root of y. So 2 minus, on the left, y to the 1/3. There's my base. Can't really simplify that, but that's okay. Let's go now and plug it into our area. So base squared will be 2 minus y to the 1/3 squared. Now, if you do wish to square all of that, remember to FOIL. Let's go ahead and plug that into our volume. Integral of the area, and area is 2 minus y to the 1/3 squared. Now, remember that we're with respect to y, therefore we need limits with respect to y. So the lowest of my region in the y-axis is 0. The highest of my region in the y-axis, 8. So 0 to 8. How about a couple more? Find the volume. Now perhaps we stop there and say, okay, I know volume is integral of the area of a slice. Let's keep reading. The solid whose base is bounded by, so I'm going to draw the base bounded by those three lines. I don't want to draw over those three lines. There we go. We won't cut them off. Positive 1 is the y-intercept, and the slope is down 1 over 2. Down 1 over 2. And we get our first line. The second line, y-intercept at -1, up 1 and over 2. Okay, so it looks like they're going to intersect there, and then x equals 0 is the third one. Here's x equals 0. So I want my region to be touching those three lines that I just graphed. There it is. Let's keep reading. Cross sections. Now this is part A, because if you take a look at the next one, it's using the same base. So we're going to be using this same base in both parts A and part B. Cross sections for part A will be taken perpendicular to the x-axis. So I'm going to draw a representative slice like this, perpendicular to the x-axis. And they are isosceles right triangles. But we can't just say an isosceles right triangle since the sides of them are not all the same length, we have to specify which is the side that's along the base. In this case, it's the leg that lies along the base of the solid. So when I take out and look at it from the front, one of the legs is along the base of the solid. So here is a right triangle. This is the part that's sitting in our cake or bread pan right here. That, if I call that B, that base length, is the leg. And that means this side is congruent to it because it's an isosceles right triangle. Now, if I need the area of the slice, I remember a triangle's area is 1/2 base times height. Because the base and the height are the same, since it's isosceles, I can simply write 1/2 base times base, or base squared. That's because the height is the same as the base. Let's figure out the length of the base. Well, it's going up and down. So I know to measure the base, top minus bottom, which gives me a clue that I'm going to be working with respect to x. What else gives me a clue that I'm going to be working with respect to x? This right here, perpendicular to the x-axis with respect to x. Now we can plug in top function is that line that we graphed first, -1/2 x plus 1. Bottom function, the line we graphed second, 1/2 x minus 1. Of course, simplify this because it's easy to, although you don't have to, but we will. -1/2 and -1/2 is -x, and +1 and +1 is +2. Call it 2 minus x, that's easier to see. Take your base length, plug it into our area. 1/2, 2 minus x, quantity squared. Take our area, plug it into our volume. Integral of 1/2, quantity 2 minus x squared with respect to x, and now I need my limits. If I'm using x's, where does the region start? 0. Where does the region end? 2. Remember, this guy was at 1 right there. 0 to 2. Cool. Now let's look at the difference between this one and part B. So part B starts with the same base. So there's our base. This time, the cross sections still taken perpendicular to the x-axis, so still looking like this. They are still isosceles right triangles, however, now the hypotenuse lies along the base of the solid. So I'm going to call this guy B because that's the base, and when I look at the frontal view, now it's going to be like this. Right triangle, the legs still are the ones that have to be congruent, but now it's this guy that we're calling the base. So we still have volume equals the integral of area of the slice. We still know that our cross sections being taken perpendicular to the x-axis means we work with respect to x. And we still have the information that area of a triangle is 1/2 base times height. However, this time the base is not the same as the height. Let's draw in the height of this triangle. There it is right there. The height. How can we figure out what the height is in relation to the base? Well, we know that if these legs are congruent, these are 45-degree angles here and here because they're congruent. Therefore, this little guy on the right side, just right here, is also an isosceles right triangle of 45, 45, 90. Therefore, this part, this half of the base, is called b over 2. That means that these congruent legs, which I should give a double mark to, are both half of the base, b over 2. Therefore, h is b over 2. Let's revise our area formula because of this. 1/4 b squared. What's b? Well, we did that in the other one because it's the same shape of the base. Top curve minus bottom curve. Remember that was the -1/2 x plus 1 minus the 1/2 x minus 1. And remember that gave us 2 minus x. But this time we're plugging it into a slightly different area formula. Plug it in there and we get 1/4 2 minus x squared. Take our area and plug it into our volume. The integral of 1/4 2 minus x squared with respect to x. And because the base of our region is not any different, our limits still go 0 to 2. Yay!